So in this last lecture of this week, we will look at several examples of controllable, not controllable, observable, and not observable systems. To recap, in the last lecture, we had looked at a state space representation of a linear time invariant system given by the state equations, which is x dot is equal to fx plus gu. X is an element of Rn, u is an element of possibly Rm, and output equation y equals hx plus jau, where y could be a p by 1 vector. Most of the examples we looked at where u was single input and the output y was also one output. So it was single input, single output system. So we showed you that the system can be made to follow a desired trajectory if the system is controllable. And to test for controllability, we obtain this matrix QC, which has G as its first column, F into G as the second, and so on all the way up to F into n minus 1 into G. Okay, so we get this matrix QC, and Kalman's test for controllability was the following, that if the determinant of QC is not equal to 0, then the system given by x dot equals fx plus gu and y equals hx plus ju is controllable. If determinant of QC is equal to 0, this implies some states are not affected by the input u of t, and hence we cannot take those states from some initial state to another arbitrarily desired state in finite time by application of u of t. We also discussed observability. Okay, if all states are not measured and states x of t can be obtained if determinant of QO is not equal to 0. And this QO matrix is again derived from F and H. So the first column is H transpose, then the second column is F transpose H transpose, and so on. The last column is F transpose to the power n minus 1 into H transpose. And again, Kalman showed that if this determinant of this matrix QO is equal to 0, it implies some states are not connected to the output y of t. If the determinant is not equal to 0, then the states x of t can be obtained from measurements y of t. And in this lecture, I will show you several examples of systems which are controllable, observable, not controllable, not observable. So we start with a very simple example of a linear SISO system, single input, single output. So the linear system is given by x dot is equal to f into x plus g into u. In this case, f is 3 by 3. So the states are x1, x2, x3, and f is given by 0, 1, 0, 0, 0, 1, minus 6, minus 11, minus 6. Okay, and the g vector is 0, 0, 6. The output equation y is equal to hx. H is 1, 0, 0. So essentially y is x1. So we can compute the controllability matrix QC, which is given by first column is G, second column is F into G, the third column is F square into G. And we will get 0, 0, 6 from here, then 0, 6 minus 36, then 6 minus 36, 150. So if you compute the determinant of QC, we will get is minus 216. So hence the system given here is state controllable. We can also compute the observability matrix QO, which is, as I showed you, it is H transpose, then F transpose into H transpose, and then F transpose square into H transpose. And in this case, we will get an identity matrix, and the determinant of QO is 1. So it is not equal to 0. Hence, the system is observable. Next, we consider a simple linear time invariant system. So in this case, again, we have x dot equals fx plus gu. F again is a 3 by 3 matrix, which is 0, 1, 0, 0, 0, 1, 0, minus 2, minus 3. X is x1, x2, x3, and the g vector is 0, 0, 1. In this case, the output equation is not only 1. Okay, so it depends on x1, x2, or x3. So y is 3, 4, 1 into x1, x2, x3. It is still a single output, but it is not as simple as the last case where y was x1. So again, we can compute the controllability matrix, which in this case is 0, 0, 1, 0, 1, minus 3, 1, minus 3, 7. Okay, so it is G, then F into G, and then F square into G. And we can show, or we can compute the determinant of this QC matrix. It is minus 1, which implies that this system is state controllable. This is from Kalman's test for controllability. We can also obtain the observability matrix. In this case, we have to do H, okay, which is 3, 4, 1, sorry, H transpose, then F transpose H transpose, and then F transpose square into H transpose, and we will get 3, 4, 1, 0, 1, 1, 0, minus 2, minus 2. So here you can see that the determinant of QO or Q observable is 0. The second column and the last column is multiplication by minus 2. So the system is not observable. So we have a system, first one, which was both controllable and observable. Now we have a system which is controllable but not observable. So let us continue with the previous example of that LTI system, and let's find out why it is not observable. So the eigenvalues of f we can compute are 0, minus 1, and minus 2. So we make a transformation which is x equals p into z, and then we rewrite the state equations and the output equation in terms of z. So the output equation in terms of z will be y equals 3, 0, minus 1 into z1, z2, z3. Okay, so it will be y is equal to hx, so it will be h into p into z, and h into p will give you 3, 0, minus 1. So what you can see is z2 is not connected to y. So y will be some 3z1 plus 0 into z2 minus 1 into z3. So whatever you do to z2, it will not change y. So hence the system is not observable because z2 is not connected to y. Let's continue with another example. So this is a very simple linear system again. We have x as x1, x2. The state variables are x1 and x2. And we have x dot is equal to fx plus gu. In this case, F is a 2 by 2 matrix because X was only X1, X2. And the elements of F are 0, minus 0.4, 1, minus 1.3. And the elements of G are 0.8 and 1. And we will consider an output equation which is 0, 1 into X1, X2. So basically, we are only measuring X2. So the controllability matrix in this case is again G and then F into G. So 0.8, 1, and f into g is minus 0.4 minus 0.5. So you can see that the determinant of this is 0, right? This, if you multiply this by minus 2, you will get this. So the two columns are not independent. So the determinant is 0, hence the system is not state controllable. Let's look at the observability matrix, which is H transpose 0, 1, and then F transpose H transpose, which is 1 minus 1.3. So the determinant of QO is minus 1, which says that the system is observable. So here is an example where the system is not controllable, but it is observable. So apart from these mathematical and sort of, you can say, cooked up examples, let us go and see some real life examples for systems which are not controllable or not observable. So one very interesting example is that of a system which has been modeled using redundant state variables. Okay, so what do we mean by redundant state variables? So the system is actually n-dimensional, x should be n by 1, but by mistake you think that there are many more variables. So while modeling, you have chosen some extra state variables which are actually not independent. Okay, this is by mistake. And this can happen if there is a huge plant and you have many state variables. Let's say you have 20 state variables containing all kinds of variables, and then you have chosen some state variable which are actually related to the other previously chosen state variables. So let's consider state equations. X dot equals fx plus gu. X is an n-dimensional vector. By mistake, m chosen state variables are not independent. So these m z's, okay, m of these state variables denoted by z are related to the x by a into x, and z is m-dimensional. So we can now convert these two sets of equations as some x tilde is equal to f into x tilde plus g into u, and z tilde dot is equal to 0. Okay, so we can do some linear combination and choose a new set of variables, state variables x tilde, such that this is what we get, and z tilde dot is equal to 0. So essentially what happens is the state variables z are not affected by u, because you can see z tilde is equal to 0. So some of these state variables, actually z tilde, these ones, are not affected by the u, and hence the system is not controllable. Okay, so this is not a realistic example in the sense that why would you make such a mistake, but mistakes do happen. You know, while you are modeling a system, you can choose many more state variables than what is really required. Let's look at another example, which is a mechanics example. So this is an example of a cart. So there is an M1 which is rolling on some flat ground. There is another cart which is M2, and then both of these are connected by a spring K. Okay, and the motion of this first one is given by x1. The motion of the second one is given by x2. This is the direction. And then there is a person sitting here in between the two carts, and they are trying to push these two carts by applying equal and opposite force F. Okay, so he's pushing this cart by F, and this is pushing this other cart by F. Okay, and both these forces are equal and opposite. Now instead of pushing, you could have probably some kind of a jet, okay, some fluid which is coming in from somewhere here, and then it is pushing this cart by some F, and this is pushing to the right this cart by F, and to the left this cart by F. Okay, so it need not be a person. You could have a mechanical system which is applying equal and opposite forces. So for such a system, I can write the equations of motion. Okay, this is a very straightforward undergraduate set of equations where you have a mass and a spring. So we can write m1 x1 double dot plus k into x1 minus x2 is f, and m2 into x2 double dot plus k into x2 minus x1 is f. So in this case it is x1 minus x2, and in this case it is x2 minus f1 x1. So the state variables are x1, x2, x1 dot, x2 dot. Okay, so I can write x1 dot as x3, x2 dot as x4, and x3 dot I can use these two, and x4 dot I can use these two equations of motion to write x3 dot is minus k by m1 into x1 minus x2 minus f by m1, and x4 dot is minus k by m2 into x2 minus x1 plus f by m2. Okay, so this is very straightforward. Anybody who can sit down and write the equations of a motion of a mass, which is two masses connected by a spring and some forces F, one is acting to the left and one is acting to the right for these two masses. So we can rewrite in the state space form. So we have x dot equals fx plus gu. F will be this matrix 4 by 4 matrix. So we'll have 0, 0, 1, 0, 0, 0, 0, 1. This element is minus k by m1. Second element is plus k by m1. This is k by m2, and this is minus k by m2. The g vector will be 0, 0, minus 1 by m1, and then plus 1 by m2. And from f and g, we can derive the controllability matrix. So QC is given by 0, 0, minus 1 by m1 plus 1 by m2. So that is G. Then the second column will be F into G. The third column will be F square into G. And the fourth column will be F cube into G. So F into G will be minus 1 by m1, 1 by m2, 0, 0. F square into G is 0, 0, k by m1 square plus k by m1, m2. This is minus k by m1 m2 minus k m2 square, and these two expressions will be from f cube into g, and I will show you what these expressions are in the next slide. So the first expression star 1 is k by m1 square plus k by m1 m2, and the second term, okay, so this is the 2 comma 4 term, is minus k by m1 m2 minus k by m2 square. So we have all the elements of the QC matrix, and we can compute the determinant. Okay, so you can sit down and do it by hand on a sheet of paper, or you can go ahead and use Maple. You know, we have discussed this computer algebra system called Maple earlier, and we can use this. Or in MATLAB, there are these other simpler computer algebra systems, and this is a very, very simple application in computer algebra system. So we can compute the determinant, and determinant of QC will be 0. So what it means is that this system x dot equals fx plus gu is not controllable. So the natural question is, why is it not controllable? Okay. So in order to find out why it is not controllable, we use a different set of state variables. So we had used x1, which was the motion of the first mass to the right, x2, which was the motion of the second mass also to the right. Instead of that, we will use xc, which is given by m1 x1 plus m2 x2 divided by m1 plus m2. So this is the change, and delta, which is x1 minus x2. So this is xc and delta, which are linear, which can be obtained by some change of coordinates of x1 and x2. So we basically do some linear transformation from x1, x2 to xc and delta. So delta, you can see, is just x1 minus x2. And what is xc? It is some combination of mass into x1 plus mass into x2 divided by the mass. Okay. So my new state variables are xc delta and xc dot and delta c dot. Okay, so once if you convert from x1, x2, x1 dot, x2 dot to xc delta, xc dot, delta c dot, you will see that one of the differential equation is xc dot equal to 0. Okay, so what is xc dot? This is basic mechanics. What you can see is xc is nothing but the center of mass of these two. And what is delta? It is the distance between two mass. So this is the mass center and this is the separation of the two carts or the two objects on wheels. So what this is telling you is that I cannot change the mass center. So xc dot will remain same. Whatever equal and opposite force that you apply, F in both the opposite directions to the mass, the center of mass remains at the same place. So I cannot change the center of mass. So if I have a desired trajectory which says center of mass needs to go from here to here, then using F, which is U in this case, which is the control input in this case, I cannot change the center of mass. Okay, whereas the separation can be changed because only xc dot will turn out to be 0. So physically what is happening is that we have F which is equal and opposite. You can think of it as an internal force in your system. Okay, the system consisting of two masses and a spring, and this F is an internal force. So you cannot control a system using internal force. Some state variables cannot be taken from some location to another desired x of t in finite time. Let's look at another interesting example. So this is a very common and a very well-known example of a pendulum on a cart. So we have this inverted pendulum on a cart. This cart can move along the x direction. So it's like wheels. So this is a sketch of this inverted pendulum on a cart. So we have x and a y-axis. Gravity is acting this way. So this pendulum has length L. It has a mass m. And I am going to denote the center of this pivot where the pendulum is by a variable x. The angle of the pendulum, this tilting angle, is theta. So hence the mass coordinates x2, y2 can be written as x2 equals x plus L sine theta, and y2 is L cos theta. So from here we can obtain the derivatives, which is x2 dot y2 dot. So this is x dot plus L theta dot cos theta. Y2 dot is minus L sine theta theta dot. We can find the kinetic energy, which is half m. M is the mass of the cart and small m is the mass of the pendulum bob. So half mx dot square plus half m small m x2 dot square plus y2 dot square. And you can expand this and we'll get half m x dot square plus half m small m x dot square plus 2x dot theta dot L cos theta plus L squared theta dot square. Okay, this is very, very straightforward. So we have done enough equations of motion in a previous module, and we can easily derive the kinetic energy of this very, very simple system. The potential energy is given by mg into L cos theta. We can find the Lagrangian, which is Ke minus Pe, and then following the Lagrangian formulation, we take partial of Lagrangian with x dot, partial of Lagrangian with theta dot, partial of Lagrangian with x, partial of Lagrangian with theta, and then the time derivative of partial of Lagrange with x dot, and time derivative of partial of Lagrangian with theta dot, and assemble it together. And the only force that is acting is along the x direction, which is this force. There is no force in the theta for the generalized coordinate theta. So the equation of motion of this inverted pendulum on cart can be derived because I know the kinetic energy, I know the potential energy, and we can do all these partial derivatives and assemble the equations of motion. Okay, so the equation of motion looks like this. It is capital M plus small m into x double dot plus m into L theta double dot cos theta minus m L squared theta dot squares into sine theta is equal to F, and then small m L cos theta x double dot plus ml squared theta double dot minus mgl sine theta equal to 0. Okay, so these are two nonlinear equations. You can see that there is a theta dot square term, there's a sine theta. Okay, so it is a null, and L sine theta is also there. So these are nonlinear equations, and we can linearize about theta equals 0, which basically means substitute sine theta as theta, cos theta as 1, and also theta dot square equal to 0. We linearize these equations and we get this linear ordinary differential equations. So we can easily see from the first equation we'll get m plus m into x double dot plus ml theta double dot. Cos theta will be 1 and sine theta will be theta, but theta dot square will go to 0. And the second equation is ml x double dot plus ml squared theta double dot minus mgl theta equal to 0. Okay, so this equation can be written as x double dot is equal to f by m, the first one, plus mg theta by m, and theta double dot is equal to minus f by capital ML plus capital M plus small m divided by ML into g theta. Okay, so these are two linearized differential equations, second order ordinary differential equations obtained from the full nonlinear ODEs for the pendulum on a card, for an inverted pendulum on a card. So we can write this in the state space form, and the state vector is x1, x2, x3, x4. There are 4 of them, and these are nothing but x1 is x, x2 is theta, x3 is x dot, x4 is theta dot. And we can write it in the form x dot is equal to fx plus gu. What is u here? U is the force which you are applying on the cart, and F is a 4 by 4 matrix which is 0 0 1 0 0 0 0 1 0 minus mg by capital M 0 0, then 0 numerator capital M plus m into g divided by capital M into L 0 0, and F will be 0 0 1 by capital M minus 1 by capital M into L. So a natural question is this system controllable? Meaning, can I take x and theta, the state variables x theta, x dot, theta dot, from some initial state to a final state by applying this force F? Okay, so we want to test for controllability. We can obtain the QC matrix. Again, the first column will be G, second is F into G, third is F square into G, and fourth column is F cube into G. I am not writing all the terms, but you can easily derive them. And you can show that this determinant of QC is not equal to 0. Okay, so hence it is controllable with F alone. Remember, there are two variables, one is x and one is theta. There is only one force F which is sort of acting along this generalized coordinate x. Even then it is controllable. Okay, meaning, let's go back to the basic definition of controllability. I can take the system from some initial state to another final state in finite time by applying this force F. Now let us look at the observability. So we are only going to measure x. Okay, so y h is 1 0 0 this into x. So what is QO? H transpose, F transpose, H transpose, F transpose square H transpose and F transpose cube H transpose. Okay, so again we can obtain, we know what is F, we know what is H, we can obtain this matrix in symbolic form using some computer algebra system like Maple. So if you choose y as x, okay, then determinant is not equal to 0, hence the system is observable. So what were the state vectors? X, theta, x dot, theta dot. So if I just measure the position of the cart, then the system is observable. If I measure only theta, but the force is applied on the cart, so 0, 1, 0, 0, then determinant of QO is 0. So hence it is unobservable, meaning that if I just were to measure theta, then you cannot do it. We can also choose to measure only x dot, okay, which is h is 0, 0, 1, 0 into x. So again it is not observable. So basically what it means is if you were to measure the velocity, this is what is you are doing, you are measuring x dot, you are measuring the velocity, I cannot obtain all the states x. So basically it is sort of intuitively correct. If you measure the velocity, you can say that we can integrate to obtain the position of that cart. However, that is not true because we do not have the initial conditions. So we do not know what is the initial condition. So hence, by measuring velocity, and by integration, we will still not be able to find the position of the cart. This is more interesting. So we are measuring theta, not x, but it is still not observable. So think about it, why the system is not observable when you measure theta. Let's take one more example, which is a little bit interesting example. It is an extension of this inverted pendulum on a cart, but now we have two inverted pendulums. So this is the same cart. We have a force which is applied. The mass of the cart is m, and the location of the hinge of both the pendulum is given by x. The first pendulum is rotating by theta 1. It has m and L1. The second pendulum is rotating by theta 2. It is m and L2. Okay, both the masses are equal, but the lengths are different. This is L1 and L2. And the force is acting in the cart, which is along the hinge. So basically there is no moment due to this force. It is just a linear force. So again, we can derive the equations of motion of this system. So before we do that, we find the position of the first bob, pendulum bob, which is Lx1, which is x plus L1 S1. The y coordinate is L1 C1. For the mass 2, x2 is x plus L2 S2, and y coordinate is L2 C2. I can find the kinetic energy of the cart and the kinetic energy of the mass, so which is half mx dot square plus half m into x1 dot square, okay, and y, so x1 dot square and y1 dot square. And similarly for mass 2, I can find half m into x dot square plus L2 square theta 2 dot square plus 2x L2 C2 theta 2 dot. Okay, again we have seen this kind of derivation earlier, even in the last example, but we have seen similar derivations when we did the dynamics for a single pendulum. The potential energy of the system is mg L1 C1 for the first mass, and the second mass is mg L2 C2. So we have the kinetic energy, we have the potential energy. Again, we can use the Lagrangian formulation and derive the equations of motion. So the equations of motion will be three of them, because there is one cart and then there are these two pendulums. So if you do some simple calculations of finding all the partial derivatives and all the time derivatives, and then we organize it together, which I am not going to do because by now you should be able to do it very easily. You will get three such equations of motion, and these are capital M plus 2m into x double dot plus small m into L1 C1 theta 1 double dot plus small m L2 C2 theta 2 double dot minus m L1 S1 theta 1 dot square minus m L2 S2 theta 2 dot square equals to F. And for the generalized coordinates theta 1 and theta 2, we'll get m L1 square theta 1 double dot plus m L1 C1 x double dot minus mg L1 S1 equal to 0, and very similar for the second pendulum, which is m L2 square theta 2 double dot plus m L2 C2 x double dot minus mg L2 S2 equal to 0. So we have three nonlinear ODEs. We can again linearize by substituting sine theta equals to theta cos theta 1 and so on. And then we'll get three linearized equations of motion for this cart with two pendulum. So the first equation is capital M plus 2m into x double dot plus m into L1 theta 1 double dot plus m into L2 theta 2 double dot is equal to F. This is equation 1. M L1 theta 1 double dot plus m x double dot minus mg theta 1 is 0. And similarly for the second pendulum, which is m L2 theta 1 double dot plus mx double dot minus mg theta 2 equal to 0. So we have three equations in three unknowns, theta 1, theta 2 and x. So from 2 and 3, okay, you substitute 2 and 3 in 1, you will get mx double dot plus mg theta 1 plus mg theta 2 equals F. Okay, you can see that this is some mx double dot plus ml1 theta 1 double dot is equal to mg theta 1. Similarly, this is mg theta 2. So we can get rid of these ml theta 1 dot and ml theta 2 double dot here from these two equations, and you will get this. And hence we can solve for x double dot is equal to minus small m by capital M into g theta 1 minus small m by capital M into g theta 2 plus f by m. Okay, so in this example, we can get rid of, we can write x double dot directly in terms of theta 1 and theta 2. So we can substitute x double dot back into 2 and 3 and simplify. So basically what have we done? We have gotten rid of x double dot from those three equations in three unknowns. We have two equations in two unknowns. The first equation is theta 1 double dot is minus capital M plus M divided by ml1 g into theta 1 minus mg divided by capital M into L1 into theta 2 equals minus f by capital M into L1. And likewise the second equation. The second equation is theta 2 double dot minus mg by capital M L2 theta 1 minus bracket m plus m divided by capital M L2 into g theta 2 is equal to minus f by ml2. Okay, so these are two second order linear ordinary differential equations, and we can write it in state space form. And the state vector in this case is x1 is theta 1, x2 is theta 2, x3 is theta 1 dot, x4 is theta 2 dot. We have done a lot of work, but eventually this is what I want to get to. So we want to write the state equations as x dot equals fx plus gu. In this case, u is F, which is the force, and g will be 0, 0, minus 1 by ml1 minus 1 by ml2. F is a little bit more complicated. The first two rows are straightforward, which we have seen happening many times. It is 0, 0, 1, 0 and 0, 0, 0, 1. And these terms A1, A2, A3 and A4 are slightly more complex terms, not very complex, but in order to save space, I am writing A1 here, A2 here, A3 and A4. So A1 is M, capital M plus M divided by ML1 into G. A2 is mg by capital M into L1. A3 is mg by capital M into L2. And A4 is capital M plus M into G divided by ML2. You can work this out, or you can again use the computer algebra system to derive these state equations. It is not very hard. Okay, and this is a reasonably simple system as far as computer algebra is concerned. It is a nice system as far as control system is concerned, and state space representation of a mechanical system is concerned, but all these simplifications and all these writing it in the state space form can be very easily done using a computer algebra system. So let's now find out what is the controllability matrix QC. So as usual, the first column is G, second column is FG, third column is F squared G, and fourth column is F cubed G. So we know what is G, F, so hence we can obtain this controllability matrix. It turns out that the determinant of this QC is given by these complicated expressions. So it is 2pq divided by m square into L1 L2 minus q square m square into L1 square minus p square m square into L2 square, where p can be written in terms of A1, A2, and q can be written in terms of A3 and A4 like this. P is A1 by m, capital M into L1, plus A2 by capital M into L2. Q is A3 by capital M into L1, and A plus A4 divided by capital M into L2. So it turns out that the determinant of QC can be 0 if some expression involving L1, L2, PQ is 0. So 2L1, L2, PQ minus Q square, L2 square minus P square, L1 square is 0. This can be simplified as capital M square, G square, L1 square, L2 square into L1 minus L2 whole square equal to 0. Okay, this is what I wanted to do right from the beginning. I wanted to find out under what conditions that cart with two pendulum is not controllable. Okay, when is the determinant of the controllability matrix for this system is 0. And you can see very clearly it will be 0 when L1 will be equal to L2, because then this term will go to 0. Okay, so hence determinant of QC equal to 0 if L1 equals to L2. So this is what I mean by saying that there is too much symmetry. Okay, we have a mass which is translating, and that there are these two pendulums with equal masses, but the lengths are also equal. Okay, so it is in some sense very special and very symmetrical. So this system is controllable if L1 is equal to L2, and is controllable if L1 is not equal to L2. Then you could see that the determinant of QC is not equal to 0. So in the sense it is quite interesting. We have only one input, remember F, and if L1 is not equal to L2, I can control three variables, x, theta 1, theta 2. The whole system is controllable, meaning I can take this two pendulum system on a cart and I can go from one state to another state in finite time by applying one single input, which is F. Okay, if on the other hand L1 is equal to L2, then it is not controllable, and I cannot transfer from some initial state to another final state by applying F in finite time. Let's look at observability of this system. Let's assume that we are only going to measure one of the rotation of the pendulum, which is theta 1. Okay, so there is theta 1, theta 2 and x, but we are only going to measure theta 1. So h is what? 1, 0, 0, 0, because remember we have two differential equations in theta 1 double dot and theta 2 double dot, and the state variables are theta 1, theta 2, theta 1 dot, theta 2 dot. Okay, in this final form after I have gotten rid of x. So h is 1, 0, 0, and we can again find the determinant of this Q0 matrix. Q0 is H transpose, then F transpose, H transpose, and so on, and we will get it as minus A2 square, which is minus mg divided by capital M L1 whole square. This is never going to be equal to 0. G is positive, M is positive, none of the elements are 0. So the really interesting part of the story is the following. If L1 were to be equal to L2, it is not controllable, but it is observable. Okay, because we don't have any condition under which this observability matrix is singular, or the determinant of the observability matrix is 0. Okay, so with this we are going to stop examples and let's continue. So in summary, a system can be controllable but not observable. A system can be observable but not controllable. So I can cook up lots of F matrix and G matrix, and we can get all these possibilities. In a physical system, in an actual mechanical system, and not just cooked up F and G matrices and H matrices, if the motion is due to internal forces, then the system is not controllable. Okay, internal means equal and opposite, like the example which I showed you about these two carts connected by a spring and two forces being applied in the opposite direction, equal and opposite. If there is too much symmetry, this setup is very special, like that example which I gave you, L1 is equal to L2, then it is not controllable. Measurement of velocity alone is not enough to obtain position. So we can see that if I just measure the velocity and then hope to integrate and obtain the position, which is also one of the states, it is not possible because we do not know what are the initial conditions for the integration. We will revisit controllability and observability in control system design in the next module. Both this QC and QO and all these are very, very useful concepts, not only to study or analyze control system, but also to design control systems.